we're going to do a topic that I find a little bit fun as we talk about the binomial theorem. And the fun comes from something called Pascal's triangle, which is where I'm going to start and then go from there. Pascal's triangle, I first learned about this, I think, in middle school, back in the early days of the internet, when I was the only one in my school that had the internet because my dad was a nerdy person. But anyways, Pascal's triangle, it's like a triangle shape made out of numbers. And it's named for Blaise Pascal. Mathematician. They talk about him a little bit in your book. Mathematician that lived in the 1600s, French. And he made contributions in calculus, geometry, probability theory. And at the ripe young age of 19, invented the first adding machine. So something that, before our modern day calculators, in the 1600s, he invented an adding machine. Anyways, I digress. But back to Pascal's triangle. Pascal's triangle is simple as far as like how it's constructed. You start with a 1 at the top. So it's going to look kind of like a tree or a triangle. And then the next row, you put 2 1s. And then from here on out, you're going to keep putting 1s on the outside. And then you're going to take 2 numbers that are side by side and add them together to get the number underneath it. So you'll keep doing 1s. I'll go ahead and put some 1s in. I like changing colors for this. And like here, you would take 1 plus 2, get 3, 2 plus 1, get 3. And then like here, you do 1 plus 3 is 4, and 3 plus 1 is 4. So notice that you've got some symmetry going on there. But then you also have 3 plus 3 is 6. Or in that next row, you just keep going like this. Like in this row, 1 plus 4 is 5, 4 plus 1 is 5. And then you have, maybe I'll use brown, 4 plus 6 is 10, 6 plus 4 is 10. And you could keep going on and on and on. And when they talk about the rows, they talk about this first row with just the 1 as row 0. Next row is row 1, then you got row 2, row 3, row 4, row 5. And it keeps going. You can keep going forever making this triangle bigger and bigger. But you keep doing the same thing. You just 1s on the outsides and then 2 numbers at a time, add them together and put the result right underneath those 2 numbers. Now this triangle has a lot of really cool things in it. I'm not going to be able to get into all the really cool things, but one of the things I was just looking at recently was called the hockey stick identity, which is something else, related to something else entirely. But my point is, you start digging and you're going to find there's hundreds of things that are related to Pascal's triangle. Well, today we're going to look at one specific thing that's related. We're going to look at when you start trying to take expressions of the form x plus y to the n and expand them, multiply them out. And we're going to see how this relates to Pascal's triangle. Okay, so we'll come back to the triangle in a minute. But let's take x plus y, and if we just raise it to the 0 power, that's just going to get us 1. Not terribly exciting, because we're going to assume x and y are not 0. X plus y is not 0, because 0 to the 0 would be undefined. But anyways, you got some kind of value, a non-zero value to the 0 power, you're going to get 1. Then if you take x plus y to the first, you just get back x plus y, so 1x plus 1y. And if you do x plus y squared, you get 1x squared plus 2xy plus 1y squared. And you can always multiply these out if you don't believe me, but these are the kinds of things you're going to get. If you do x plus y cubed, x plus y times x plus y plus x plus y times x plus y, you get 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. If you do x plus y to the fourth, you get 1x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the fourth. And I don't know if you've spotted it yet, but you might start to see how this relates to Pascal's triangle, the thing that I just had up above. Let me do one more, x plus y to the fifth. 1x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed plus 5x y to the fourth plus 1y to the fifth. I got a little space there. That's one reason I'm not going to go any further. I hope you see it now, but if you don't, let me do this. As I draw these, I'm wondering if you're seeing it yet. But look at those coefficients. Look at what's happening as you go down the triangle. It is the coefficients are Pascal's triangle. You got 1, then you have 1, 1, then you have 1, 2, 1, then 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. If you kept going, you did the 6th power, 7th power, 8th power, you continue to have your coefficients being out of Pascal's triangle. Cool, huh? Notice also like the pattern for your x's and y's and their exponents. Well, let's just go down to that last one. Notice that for those x terms, yellow's probably not going to show up, is it? I'll make that black again, and then I'll highlight. Notice the x terms, the exponents, it's understood to be a 1 there, they count down. Like the power was 5. Notice that x started with the 5th power in the first term. Then it goes 5, 4, 3, 2, 1, 0. You don't see the 1 because we don't write it, and then you don't see x to the 0 because that's just 1. And then notice for the y's, you know, those count up. Basically, technically, they start with 0, and then 1, 2, 3, 4, 5. So the highest exponent is the same as the exponent that was outside the parentheses, that, you know, you're raising that to the 5th power. Also notice that the numbers of terms is 1 more than whatever power you're doing. So like when we did x plus y to the 5th power, we ended up with 1, 2, 3, 4, 5, 6 terms. So there's all kinds of patterns deep within this. But that's not all. There is more. Let me show you. Let's just focus on this x plus y to the 5th power. Let's look at that second term and look at that coefficient of 5. Notice that the exponents are 4 and 1. A really cool thing is that on this one, you can do 5 factorial over 4 factorial times 1 factorial, and that equals 5. If you don't believe me, you can put it in your calculator, Or we'll work it out. 5 factorial means multiply 5 times all the integers below it to 1. 4 factorial means the same thing, so 4 times 3 times 2 times 1. 1 factorial is just 1. I can either multiply and reduce it, or I can recognize that I actually have some common factors here. I don't really need to worry about the ones. So I do end up with 5. Interesting, huh? Now what about that? So that was the coefficient of 5. Let's go to the next coefficient of 10. 10 is actually equal to 5 factorial again, over. And then notice the exponents on the x and y. You have a 3 and a 2. If you put 3 factorial, 2 factorial on the bottom, that actually makes a true statement. That does equal 10. Like if you do 5 times 4 times 3 times 2 times 1 in the numerator, 3 times 2 times 1, and then times 2 times 1 in the denominator. You have a bunch of stuff that reduces. So then you have 5 times 4 over 2, 20 over 2, which is 10. So there's actually something to be said for this too. For each of the terms, you can do for your coefficient, you can do whatever the power is, like x plus y to the 5th power. That factorial goes up top, and then those 2 exponents, the factorials go on the bottom. And that'll work that out, and that gives you the coefficient. Pretty neat, huh? So let's say you can generalize this. Let's say you have x plus y to the n power. Okay. If one of your terms is of the form x to the r, y to the n minus r, then the coefficient is n factorial over r factorial times n minus r factorial. So that's another thing to notice, that n minus r. Notice that in each of our terms, those exponents added up to that 5. So if one of your exponents, let's say, is 2, then the other one has to be 5 minus 2 or 3 for this. That's the whole r and n minus r thing. So it's just a fancy way of saying that, like, whatever your power is for that binomial exponent, that factorial goes up top, and then whichever, when you're looking at that particular term, you're trying to find the coefficient, your exponent on the x factorial goes on the bottom, and your exponent on the y factorial goes on the bottom. But if you let x's exponent be r, y's exponent has to be n minus r. Okay, and let's take this one step further. Hopefully you've already watched my videos on permutations and combinations. Because if you have, you might recognize that our formula here is the same as the formula for combinations. What's not in my video is that another way to indicate we're trying to find a combination is this kind of notation. It looks like giant parentheses with n and r in there. So that giant parentheses with nr means the same thing as ncr. And you can do these in your calculator. Some calculators, it's like on the actual buttons, you'll be able to see it like as a second menu or something. Other calculators, you might have to push a PRB button for probability to pull up this option. Then the Desmos scientific calculator, you have to push other options to get to it, but it does exist in there too. All right, well, let's just do a couple of examples of these binomial coefficients. So evaluate each binomial coefficient. Okay, so let's say we have this. That's the same thing as finding the number of combinations of n objects choose, or if 9 objects choose 5. So we're going to have 9 factorial over 5 factorial, parentheses 9 minus 5 factorial. So that's 9 factorial over 5 factorial times 4 factorial. You can put that in your calculator, and if you do, you might want to just make sure you put parentheses around these two, around that denominator. But you can also realize if you work it all the long way, you have 9 times 8 times 7 times 6, and you can stop there because the rest of those numbers will reduce with the 5 factorial on the bottom. And we can skip the 5 factorial on the bottom because that would have reduced, and we can just do 4 times 3 times 2 times 1 for 4 factorial. 3 times 2 is 6, so those two reduce. 4 goes into 8 twice. So what do we got? 9 times 2 times 7, which equals 126. So that's how we would do something like that. Oh, what if this comes out the same number? That should be interesting. 25 factorial over 25 factorial times 25 minus 25 factorial. Well, 25 factorial over 25 factorial, we know it's just going to reduce to 1. But we still have that matter of 0 factorial. Well, 0 factorial, by the definitions of factorial, is actually just 1. So the answer is 1. So yeah, just remember that 0 factorial is 1, not 0. If you had 16, 0, you'd have 16 factorial. But notice what happens here, 16 minus 0 factorial times 0 factorial. So you end up with 16 factorial over 16 factorial, 0 factorial. So you end up with 1 again. Or they could write it like this with the C. So 15 factorial over 8 factorial times 15 minus 8 factorial. So you end up with what? 15 times 14 times 13 times 12 times 11 times 10 times 9. You can stop there because everything else will reduce with 8 factorial. And on the bottom we have 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1. Some of this stuff will reduce. So you end up basically with what? 15 times 13 times 11 times 3. Or you can just do it in your scientific calculator. Yeah, the scientific calculator I'm using right now has actually I have to push the second key and then there's an NPR or NCR option. But right now, if I just multiply those together, I get 6,435. But I'd get the same answer if I use the little NCR option on the calculator. Okay. So Pascal's triangle, I'm going to scroll back up, hope I don't make any of you dizzy. Again, I mentioned earlier it has some symmetry to it, which is kind of interesting. And then if you look at these, there's symmetry as well. And when you start to look at how the Pascal's triangle and the coefficients all relate to this binomial theorem, you'll see that there's some relationships here too. Like you have 5x to the fourth y to the first, but then you also have 5x to the first y to the fourth. So you basically got two of these binomial coefficients that come out the same. So that's kind of interesting. You've got 5 factorial over over 4 factorial times 5 minus 4, and then you got the 5 factorial over 1 factorial times 5 minus 1 factorial. So it's kind of fun how these things come out the same. This is the same thing as this. Because if you work it out, like if you do the formula, you have n factorial over r factorial times n minus r factorial for this one. And if you work out the formula over here, you got n factorial over n minus r factorial, and then n minus r factorial is going to be r factorial. So they ultimately come out the same. And that's the reasoning behind, too, the mathematical justification for looking at the Pascal's triangle and seeing that symmetry. Okay, so what are some other observations here? Well, this expansion of x plus y to the n power, here's some observations. There's going to be n plus 1 terms in the expansion. Okay, let me do an example. So if you have x plus y squared, you'd have 1x squared plus 2x first y first plus 1y squared, like that. So like the n is 2 in this case. So then there's 2 plus 1 or 3 terms in that expansion over here. That's going to be the case each time. The first term is x to the n. So the first term in this case was x squared. Last term is y to the n. In that case, y squared. In each succeeding term, exponent on x decreases by 1. And exponent on y increases by 1. So like you look at that expansion example up there, x's exponents go 2, 1, and then 0. We don't actually write x to the 0 at the end there, but it's there. And then for the y's, it goes 0, 1, and then 2. The sum of the exponents on x and y in any term is n. So like if n is, since x plus y squared, n is 2, so each term, your x and y exponents will add up to 2. So we have just x squared, or x2. Then in the other one, we have x1, y1. 1 plus 1 is 2. In the last one, we have y to the 2. So we get 2 again. And then the coefficient of the term with x to the r, y to the n minus r, or x to the n minus r, y to the r, so there's that symmetry situation, is going to be, you do the combinations of n and r, in CR. So all of these observations suggest the binomial theorem. Okay. Any positive integer n and any complex numbers x and y x plus y to the n equals x to the n plus you can keep going. So this is just a fancy like mathematical way of saying what's going on here. Notice when you're trying to find the coefficient, the top number is the n, or the exponent that the binomial is being raised to. And notice how the first position is a 0, second position has a 1, third position has a third term has a 2, etc. Also, okay, so to also notice not only is that, but the top number is always n, then the bottom number matches up with that exponent on your y. So that's something to notice too. All right, well, let's try this. Let's use this. And let's take x plus y to the 8th power. And let's write the binomial expansion of that. Well, in this case, we know n is 8. So let's see what we got here. We know the first term has to be x to the 8th. And we also know there's going to be 9 terms, because there's always one more. If the exponent there's 8, or n is 8, then you're going to have one more than that for the number of terms. But then we got to do this. So our x's, the exponents are going to count down. The y's, the exponents are going to count up. And then for the coefficient, we're going to have 8. And then on the bottom, we're going to basically have the same as the exponent on y. You'll notice I'm kind of being quiet because I'm trying to concentrate here. I feel like it's so easy to make a mistake with my numbering, miss something. You could write 8, 8 on the end there, but 8, 8 comes out to 1. And at the beginning, I mean, I'll go ahead and write it. At the beginning, we could have written 8 and 0, but that also comes out to 1. So it's not really necessary to write it, but I mean, the pattern does continue. Technically, it starts with 0 on the bottom and then goes 1, 2, 3, 4, 5, 6, 7, up to 8 on the bottom. And it's always 8 on top. And when you actually work those out, like you can put them in your calculator if you want, or you can do Pascal's triangle if you really want. But you're going to end up with 1 x to the 8th. Then you're going to end up with plus 8 x to the 7th y plus 28 x to the 6th y squared plus 56 x to the 5th y cubed plus 70 x to the 4th y to the 4th plus 56 x cubed y to the 5th plus 28 x squared y to the 6th plus 8 x y to the 7th plus 1 y to the 8th. And that would be your expansion. Same result you would have gotten if you'd gone down into the 8th row of Pascal's triangle. That would have given you those same coefficients. Now, if they throw you something a little different, you got to be careful. Like, they don't always just throw you x and y. They might throw you something like m over 3 minus n to the 4th power. Okay, so now we're not just dealing with plain x, plain y. We're dealing with m over like 1/3 m, or m over 3, and we're dealing with a negative 1n. So it's a little more exciting. So now you still have the same rules for your coefficients. So like the first one's going to be 1, but that m over 3 is what's being raised to the 4th power in that first term. So keep in mind n is 4. So then you're going to have, all right, you'll have 4, 1. You're going to have 5 terms altogether. So let me go ahead and write this out. You'll have 4, 2. You'll have 4, 3. And then the very last one, you're just going to have whatever that negative n to the 4th power. Okay. So in the second term, you're going to have the m over 3 cubed and the negative n to the 1st power. Then in the next term, you're going to have m over 3 squared and the negative n squared. Next term, you're going to have just m over 3 to the 1st power and negative n cubed. And then the last term, you'll have the negative n to the 4th power. So the m over 3 is taking the place of x. The negative n is taking the place of y in the previous examples. But the rules as far as the exponents, the way they count, like for the m over 3, they count down, 4, 3, 2, 1, 0. For the negative n, they count up, 0, 1, 2, 3, 4. And then the coefficients still get worked out the same way. But it gets a little more exciting because now you have m over 3 to the 4th power. Well, that's m to the 4th over 9, 27, 81. Plus, okay, so my 4, 1, that was 4. And then m cubed over 27 times negative n. Plus, and then my 4, 2 is 6. And then I've got m squared over 9. And negative n squared is just n squared. Plus my 4, 3 is 4 again, which makes sense. This should be symmetric. So since I had a 4 in the second term, I should have a 4 in the 4th term also. All right, so that 4th term, I've got just m over 3, but negative n cubed. So that is still going to give me like negative n. So negative 1. So this can change to a negative, and then I could just say n cubed. And then plus negative n to the 4th is going to be n to the 4th. Goodness, got some more cleaning up to do. All right, first term, m to the 4th over 81. Second term is going to end up being minus because you have a plus 4, but then you have that minus n. So it's going to end up being minus. You could say 4 over 27, and you could say m cubed n. Then plus, well, 6 over 9 is 2/3, m squared n squared. Then you end up with minus 4/3 m n cubed plus n to the 4th. And there you go. So now you can see your m's count down, 4, 3, 2, 1, 0. Your n's count up, 0, 1, 2, 3, 4. But your coefficients are a little different because of that m being over 3 originally. So you had to raise the 1/3 to a power and then multiply by your coefficient. And then for the n's, notice the signs alternate because you had a negative in. So negative 1 to raise to an even power is positive 1, but negative 1 raised to an odd power is negative 1. So like the second term and the fourth term all involve those odd powers. So you end up with negatives in there. So there's that. Let's see here. Maybe do one more of those. Before I do one more of those, let me do a little comment. The binomial theorem earlier, you can also use summation notation to write it. If you do an x plus y to the n power, you could write it as the sum of r equals 0 to n, like that. So just be aware, it can be written that way too. Or you can write it out the expanded way and say x to the n plus, and then the n choose 1, x to the n minus 1y plus, and choose 3, x to the n minus 3y cubed, and so on. But this is a way to just write it with summation notation instead of like starting with r equals 0. So your first term you'd have n, whatever your n is, n choose 0, x to the n minus x to the n, and then y to the and then 1, y to the 0 is 1. Then the next term would be n choose 1, x to the n minus 1, y to the 1. Then the next term would be n choose 2, x to the n minus 2, y squared, etc. So that's just something to kind of keep in mind. Okay, so let's do this. Let's expand 2 over r cubed plus 4 over square root of r. That's not going to be very fun, is it? And the whole thing's being cubed. At least we don't have as many terms. We'll just have 4 terms to worry about because n is 3. There's always one more than that. All right. So for our first one, yikes. This is pretty weird, isn't it? All right, so for that first one, we'll just have 2 over r cubed. And for our next one, okay, we'll have 3 and 1. And then we'll have 2 over r cubed squared and just 4 over square root of r. Then for our next one, we'll have 3 choose 2. We'll have 2 over r cubed to the first power, and then 4 over square root of r squared. And then for the last one, it's just going to be 1, 2 over r cubed to the 0 power, so we don't have to worry about that, and then 4 over square root of r cubed. Ooh, goodness. You'll probably find that your book likes to go ahead and just use like fractional exponents to make things a little easier. So instead of square root of r, they'll say r to the 1/2. Keep in mind, square root of r is the same thing as r to the 1/2 power. Okay, so that first term, 2 cubed is 8. R cubed is r to the 9, because you have 3 times 3 in the exponents. Plus, and then the 3 choose 1. Let me put that in my calculator real quick here, because I just don't really remember off the top of my head. It's 3. I should remember that. Then you got 4 over r to the 6th, and then 4 over r to the 1/2. So we'll keep it that way. Plus, and then it has to be symmetric, so this 3 choose 2 must also be 3. Yep. 2 over r cubed times 16 over r, because square root of r squared is just r, plus 64 over, well, r to the 1/2 cubed is going to be r to the 3/2. So there's that. All right, a little more cleaning up. 8 over r to the 9th plus 3 times 4 times 4 is 48 over r to the 6 times r to the 1/2. 6 r to the, you don't really say 6.5, instead you say 13 halves. Plus 3 times 2 is 6 times 16 is 96 over r cubed times r is r to the 4th. Then plus 64 over r to the 3 halves. Ooh, that was a lot, wasn't it? But there you go. All right, one last concept, wrapping it up. Kth term of the binomial expansion. If you have x plus y to the n, and your n is greater than or equal to k minus 1, then the kth term is this. Okay, let's go back to x plus y cubed. I feel like I need a little more to go on with this. X plus y cubed, I had what, 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed, right? Yeah, because the Pascal's triangle, 1, 1, 1, 1, 2, 2, 1. Let's see. Oh, goodness gracious. Make sure I did that right. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Yeah, okay. Just making sure. So what is this saying here? Well, as long as your n is bigger than k minus 1. All right, so like in our case, the n is 3, right? So you've got your various terms here. So let's say you're looking at that second term. So it's saying that if you didn't know what the second term was, you could find it by doing 3, and then 2 minus 1, which is 1, and then x to the 3 minus 2 minus 1, and y to the 2 minus 1. So that 3 choose 1 will give you 3, and then x squared, y to the first. So you got your first, k is what number term you're trying to find. K equals 1 would be the first term, k equals 2 is the second term, k equals 3 is the third term, k equals 4 is the fourth term. You know, and as long as your n is greater than or equal to that term minus 1, you're good. If you think about it, all right, so you're cubing this. Well, you've got 4 terms. Your fourth term would be 4 minus 1. 4 minus 1 is 3, and your n is 3, so you're good. So for any of these, you can figure out what that term looks like by taking the combinations of n and k minus 1, n combinations k minus 1, and then looking at your exponents in that pattern. So within that little combinations statement, subtract the two numbers. That'll give you your x exponent, and then the bottom number will give you the y exponent. All right, let me do one little more general example. Let's say you have 2c minus d to the 12th power. Okay, so we definitely know that n is 12. And we're trying to find the fourth term. So our k is 4. If you do k minus 1, 4 minus 1 is 3. That's definitely less than n, which is 12. You know, that's part of the little rule. But anyways, so we're going to use that formula. That looks like this. Okay, so we got 12 on top, and then k minus 1 is 3. Then x to the, like if we know k minus 1 is 3, then x is going to be to the 12 minus 3, which is 9. And then y is going to be to the 3. Okay, so do, and you can do it in your calculator, 12, and then my NCR, 3, and I get 220. So I get 220 x to the 9 y cubed. But notice that we've actually got a different situation here with the 2c and the negative d. So it's not enough just to use x and y. We got to consider 2c and negative d. So our answer is going to end up being negative something, because the negative cubed is still going to be negative. We're going to have a c to the 9. Then I got to do 2 to the 9th power times 220. And I get 112,640. So this is my final answer. Fun stuff, huh? Maybe we can do one more of those. I feel like we need to do one more. I'm going to pull one out of the book. Let's say we have 2c minus 3d. What numbers did I just use? Well, whatever. 2c minus 3d, and we're raising this to the 14th power. So this is definitely different. All right. And this one, they're asking us to find the 8th term. Okay, so my n is 14, my k is 8, k minus 1 is 7. So let me rewrite the formula. All right. So I use the n, which is 14, and then the k minus 1, which is 7. X in this case is 2c. And then that's raised to the n minus k minus 1. So in other words, look at your numbers in the parentheses there and subtract those. 14 minus 7 to get that one. And then y is that same number that's on the bottom there, the 7. So you're going to have 2c raised also to the 7th power and y to the 7th. Okay, so let me do the 14 NCR 7. I get 3432. And then I still have to worry about 2c to the 7th and y to the 7th. Well, 2 to the 7th power is 128. So I've got the 3432 times 128 times c to the 7th times y to the 7th. So let's times that 128 by 3432. I think my calculator doesn't have it quite right here. Did I already do that? Yeah. Okay, so 3432 times 128. I haven't dealt with the y yet. Oop. Y is negative 3d, isn't it? Oh, okay. It's going to be a big number. I still got to account for that. Goodness. So whatever negative 3 to the 7th power is. Negative 2187. So I got to multiply that with the 439,296. That's a big number. I think your book just left it kind of factored, and now I'm seeing why. They left it as like 6 to the 7th power and then times the negative 3432. So you get the same thing, but I can see why they did that. I have the teacher's edition, of course, and they left the answer like that. But here you go. So just make sure you go back and keep in mind that x and y, like in this one, the 2c was your x and the negative 3d was your y. But that would be that term. Can you believe that coefficient? Yikes. Aren't you thankful they didn't ask you to do the full expansion on this one? Fun times, right? Okay. Well, I think that's enough of that for now. That's basically what you need to know about the binomial theorem. And for this course, we've only got one more lesson to worry about, and that is proofs by mathematical induction. So that should be made soon and added to YouTube if you're in the current semester. If you're into the future, then you should already be able to see it on YouTube. But anyways, thank you for joining me, and hope you have a fabulous day.